Superradiance, unveiling quantum synchronization in free space. Quantum physics has always been a domain of wonder and intrigue, brimming with phenomena that challenge our understanding of reality. Among these, superradiance, a synchronized burst of light emitted by atoms, stands as both a captivating and elusive concept. While this phenomenon has been observed within confined optical cavities, its realization in the infinite expanse of free space has long remained an unresolved question. Recent advancements, however, have brought us closer to deciphering how atoms might achieve synchronization in such an open environment. This isn't just a milestone in theoretical exploration. It could revolutionize our interaction with the quantum world. At its heart, superradiance is about harmony. Within optical cavities, atoms and photons interact in a manner that aligns atomic emissions, creating a burst of energy far greater than the sum of individual emissions. The reflective walls of the cavity facilitate this by forming a feedback loop. Photons bounce back and forth, synchronizing the atom's emissions to produce an amplified collective output. However, the dynamics shift drastically in free space. Without reflective boundaries to guide them, photons scatter in all directions, and atoms emit light independently, much like musicians playing without a conductor. This absence of coordination prevents synchronization, making superradiance appear unattainable in such an unrestricted setting. The challenge of achieving superradiance in free space goes beyond technical obstacles, delving into fundamental questions of physics. Can independent atoms exhibit collective behavior without external constraints? A recent experiment aimed to tackle this profound question. Researchers arranged a pencil-shaped cloud of ultracold atoms in free space and excited them with a continuous laser, seeking evidence of synchronized emissions that could suggest free space superradiance. Initial observations were compelling. Signs of partial synchronization emerged, with some atoms aligning their emissions, hinting at the possibility of superradiance in free space. Yet, these findings sparked debates. Was this genuine superradiance or merely a coincidental alignment under specific conditions? To explore further, theoretical physicists conducted advanced simulations, modeling each atom as a dipole capable of absorbing and emitting photons. These simulations recreated the experimental setup and provided deeper insights. The results revealed that the observed partial synchronization was not true superradiance, but rather a result of specific experimental parameters, such as the density of the atomic cloud and the intensity of the laser. Anna Maria Ray, a leading theoretical physicist, explained the complexity of the problem. In many cases, interactions are weak enough for simplified models to suffice, but it wasn't initially clear if that applied here, she noted. Graduate student Sanat Agrawal, the lead author of the study, elaborated. We used a microscopic model where each atom acts like a dipole to study the emergent properties of the entire cloud. The laser's phase pattern played a crucial role in determining how the atoms interacted. The team simulated various conditions, including changes in laser power and atom density, to understand the factors influencing synchronization. Their findings showed that a mean field approximation, treating atoms as classical magnets, was sufficient to replicate the observed behavior in the dilute regime. However, Ray emphasized that future research would need more sophisticated models to tackle dense and highly interactive systems. This collaboration between experimentalists and theorists highlights the power of combining observation and rigorous simulation to bridge gaps in understanding. By refining foundational theories like the Dicke model, which first described collective atomic behavior, this research pushes the boundaries of our knowledge of light-matter interactions. The study also draws parallels with Bose-Einstein condensates, where particles achieve synchronization at extremely low temperatures. Additionally, the concept of spontaneous symmetry breaking, often observed in condensed matter physics, provides a potential framework for understanding how partial synchronization transitions to full superradiance in free space. The implications of this research extend beyond theory, inspiring new experimental designs. Adjusting the density or geometry of atomic clouds, or employing advanced optical techniques to control photon pathways, could create conditions more conducive to synchronization. Meanwhile, developing quantum-level simulations for complex systems remains a critical next step. This work underscores a broader truth about science. Progress is driven by bold questions and the exploration of the unknown. The quest to understand superradiance in free space exemplifies the power of curiosity and collaboration, challenging us to rethink assumptions and venture into uncharted realms of quantum physics.